So far, we have only talked about the shadow prices for the less than or equal to constraints. Now, what if the sign of the constraints are greater than or equal to an equality constraint? So let's start. So in this example, Steelco has received an order for 100 tons of steel. And these are the constraints. This order must contain at least 3.5 tons of nickel. So among this 100 tons, 3.5 of them must be nickel, at least, sorry. And then at most, 3 tons of them must be carbon and exactly 4 tons of them manganese. Steelco receives $20 per ton for the order. And then to fill the order, Steelco can combine 4 alloys. So combining these 4 alloys such that the sum becomes 100 tons of steel. But the composition of each alloy is different. For example, the first alloy contains 6% of nickel, 3% of carbon, and 8% of manganese and costs $12 per ton to produce. Formulate the LP to maximize the profit. So here are our decision variables. The number of tons of alloy I used to fill this 100 tons order. Of course, the sum must be exactly 100 because the order size is 100 tons. And then for the other constraint, for example, nickel constraint, because the first alloy contains 6% nickel, so you see 0.06 here. It means 6% of X1, the amount of alloy 1 that you used, contains nickel. And then 3% of X2, so 0.03 here, 2% becomes 0.02, and finally 1% of alloy 4 is nickel, so 0.01 X4 must be greater than or equal to 3.5. Okay, I will pause the video so you have the time to look at this example carefully to get the context and also look at the formulation. So this is the primal problem, and we're given the information of the optimal table. Well, not really the table, but the important information is here. This is the optimal row 0. So the steps will be the same as before. We are going to use this optimal row 0 to obtain the optimal dual solution. From the optimal dual solution, we get the shadow prices. So the primal is a maximization problem, so we're going to use this guideline to obtain the dual solution. Okay, we have 4 constraints in the primal, so we will have 4 variables in the dual. And then these are the values for the optimal values for each dual variable. For y1, because the first constraint in the primal is greater than or equals to, we are going to read the coefficient of e1 in the optimal row 0 and put a minus sign in front of it. So the coefficient of e1 is 400. With a minus sign, it becomes minus 400. And that's the value, the optimal value for y1. For y2, because the second constraint is less than or equal to, we're going to read the coefficient of s2 in the optimal row 0. But this is the optimal row 0, you don't see any s2. It means that the coefficient of s2 equals 0, so the optimal value for y2 is also 0. For the third and fourth constraint, they are equality constraints, so we need to read the coefficient of A3 and A4, but then minus m, put the minus m to the coefficient. So for A3 it becomes 200, and then for A4 it becomes 16. I mean the value for y3 becomes 200, the value for y4 equals 16. So we have obtained the optimal dual solution. Based on the optimal dual solution, we know that for a maximization problem, the shadow price of the ith constraint equals the optimal value of the ith dual variable. So we have obtained the shadow price of nickel, carbon, manganese, and order size. The shadow price for nickel is minus 400. And then if we know that B1, the right hand side of nickel, is between 3.46 up to 3.6, then the current basis remains optimal. So if we change B1 from 3.5 to become 3.55, which means the change is 0.05, then we may compute the new Z value using this formula. For maximization, it is equal to the optimal Z value plus the change times the shadow price. So the new optimal value with respect to this change equals 1000, the optimal Z value, plus the change 0.05 times the shadow price minus 400. So it becomes 980. So if we increase the right hand side of the nickel constraint from 3.5 to become 3.55, then the Z value actually will decrease from 1000 up to 980. This may be explained because in a maximization problem, if we increase the right hand side of a greater than or equal to constraint, actually this makes it harder to satisfy the constraint, right? In other words, it makes the feasible region stays the same at least or even smaller than before. Imagine that in the original problem, the nickel constraint says that you must produce the order with the nickel constraint at least 3.5 tons. Now the requirements is increased. Your order must contain at least 3.55 nickel. So it is getting harder, right? That's why the feasible region at least stay the same or even smaller. And then as a consequence, the shadow price of a constraint with greater than or equal to sign in a maximization problem must always be non-positive. It means increasing the right hand side of this kind of constraint will never increase the Z value. At least the Z value will be the same or even decreasing because it is getting harder. The requirements is getting higher. For carbon constraint, the shadow price is 0, and then suppose we know this is the boundaries for carbon constraints such that the current basis remains optimal. So if B2 increases, currently 3, and then if it is increasing to 3.1, 4, 5, 6, or even 100, it doesn't really affect the Z value because the shadow price is 0, and then we may increase B2 up to infinity and the current basis remains optimal. This may be explained by the fact that we still have slack, right? So we only use carbon up to 2.75, so it doesn't matter if the carbon right hand side is 3, 4, 100, infinity. It doesn't matter because in the current optimal solution we only consume up to 2.75. We still have the slack of 0.25 to the current right hand side, so the increase will not affect our Z value. For the manganese constraint, the current basis remains optimal if B3 is between these values. So suppose we increase the manganese constraint from 4 up to 4.5, then we may recompute the new Z value, and then we obtain that this increase causes the Z value to increase to become 1010. Finally, for the order size constraint, the current basis remains optimal between these values. So if the order increases from 100 to become 103, the Z value increases as well to become 1048. In general, the shadow price of an equality constraint can either be positive or negative. Because if you recall, the dual variable of an equality constraint has a sign restrictions of URS. and then the dual variable is related to the shadow price. In the maximization case, they are the same. Okay, so if the dual variable has the sign restrictions of URS, it means that sometimes the shadow price of this kind of constraint can be positive, sometimes it can be negative. We cannot say for sure which one. Okay, so that's the end of all the topics that I would like to discuss this week. Thank you for watching all the videos. And next week, we are going to still talk about duality with respect to how we may use this dual theorem result to perform sensitivity analysis. And then we are going to talk about dual simplex as well. Dual simplex will be useful for the change in the right-hand side. Okay, so see you next week. Thank you.